Okay, we're going to be starting chapter 6 here today. This first section in chapter 6 deals with what are called random variables, and we're going to be discussing two different types of random variables, discrete and then continuous. What a random variable is it's often denoted by a capital letter, can be X, Y, but it's a variable whose possible values are numerical. Okay, they're definitely numerical outcomes of some random phenomenon. Okay, so as I mentioned, there are two types of random variables, discrete and continuous, and we're first just going to focus on what a discrete random variable is and kind of talk about some specific examples here. Okay, so a discrete random variable is one that can take on what we call a countable number of distinct values. You can kind of think of it like this. Typically, a discrete random variable is something where there can be gaps in between the numbers. So here's some examples. The number of people, or number of children rather, in a family. So there could be 2 children, there could be 3 children, there could be 4 children. There's obviously gaps in between 2 and 3, like all of the decimals and fractions in between there are gaps, okay? Friday night attendance at a cinema, okay? The number of patients that a doctor sees a day, okay? Now, don't think that discrete means that it can't be a decimal. It's really more about, can there be gaps in between? Okay, so for example, shoe size. We know that shoe sizes, someone could wear a size 7, someone could wear a size 7.5, but there's not really any shoe sizes between a 7 and a 7.5. So that's what we mean by saying that there are definitely some gaps in between those numbers. Okay, let's look at some specific examples here. Okay, the random phenomenon that's happening in example 1 is that we were to roll a die, and then what we're going to be doing is we're going to be observing the side of the die that is facing up. Okay, the task for part A is we would record whether the face is showing an even or an odd number. Okay, so we're not recording what the number is, we would be reporting whether the number is even or odd. The question is this a random variable? Okay, and we're going to respond to that it is not a random variable because the thing that we're reporting is actually a word. It's not numeric. It's not quantitative, and random variables are quantitative. So we're going to say no because the words even and odd are not numerical. Okay, random variables are numerical in nature. Okay, so let's take the same random phenomenon, but now this time we're asked to record the actual number showing on the side that's facing up. Again, the question is this a random variable? Now for this one, we would say yes, it is, because it is numerical. Okay, so it's all about, what are we reporting here? Okay, so if a discrete random variable can have gaps in between the values, when we talk about a continuous random variable, this would be a random variable which could take on an infinite number of possible values. Okay, you want to kind of think of a continuous random variable as being a measurement. Okay, when you think about measuring something, for example, someone's height or someone's weight, or maybe the amount of sugar that is contained in, say, an orange, these are values that could really take on an infinite number of decimals, fractions across a range there. Okay, so these are examples of a continuous random variable. Okay, let's take a look at example number 2 here. It says, imagine selecting a U.S. high school student at random. We're going to define X, this is our random variable, to be the number of languages spoke by the randomly selected student. Okay, once again, take note here, we would be recording a number, so this is definitely numerical. It says the table below gives the probability distribution of X. Okay, so essentially what you see here in this probability distribution is you can see the number of languages spoken. This is our random variable. So I'm going to just off to the side, we're going to call that X. I'm going to put a little sub I because someone could speak 1, 2, 3, 4. We've got 5 different languages in this table. And then underneath those numbers represents the likelihood or probability that a randomly selected student would speak that number of languages. Okay. For number 1, it says, can languages be considered a random variable? Explain. Okay. So we're going to say no, because the type of language is not numerical. Okay. So if we're talking about like the actual language that someone speaks, that is not numerical in nature. Okay. Is this a legitimate probability distribution? If you remember, when we're checking to see if a probability distribution is legitimate, it takes 2 things. 1, the probabilities all have to sum up to be the number 1. Okay, so we're including 100% of the likelihood here. And each of the individual probabilities all have to be values between 0 and 1. Okay, if you were to go through and add up those 5 numbers, we would discover that yes, indeed, the probabilities sum to 1, and we can see that they are all between 0 and 1 as well. So that is certainly a legitimate probability distribution. Okay, part C says, make a histogram to display a picture of the distribution of the number of languages that a U.S. high school students speak. Create this by hand, and then it mentions to create this on the calculator. Okay, so when we're doing this by hand, we would construct our kind of quadrant 1 here. Okay, we always want to keep in mind anytime in AP Stats that we are making any sort of graph, it is crucial that we are always labeling our X and Y axis. So the number of languages is what we're going to place along the X axis, and the probability is what we're going to place along the Y axis. Okay, and we want to make sure that we go all the way up to including 100% of the probability. Okay, and then we would just simply take a look at what we have here in our probability distribution, and we would make these bars go up to the height of what the probability is. Okay, so we're roughly estimating about 63% for one language, almost 30% for 2 languages. Looks like we're about 6% for 3, and then we're really, really small likelihoods here as we span out to 4 and 5 there. Okay. Now, if we were going to construct this on the calculator, I will place a short video under the tab TI-84 videos of how to construct a probability distribution on your calculator. Of course, you would place the languages in L1 and the probabilities in L2, but there is something special that we would need to do in one of the settings here. So you can access that video on my webpage. Okay, let's move on down here to this probability question. We can tell this is a conditional probability. They are asking us to find the probability that, remember this vertical bar means given. Given that the number of languages spoken is more than 1, what is the probability that someone is speaking 3 or more languages? Okay, and then we always want to make sure we're reading the directions carefully. It's good to underline or circle anytime they're asking you to then interpret the meaning, because that's easy to just kind of overlook that. Okay, so if you recall, this conditional probability formula is a formula that is definitely on the formula sheet. Okay, when you have this given notation, the formula is the intersection of your 2 probabilities goes in the numerator, and then just the probability of only the given portion is what goes in the denominator. Okay, so we would want to be saying here, what is the probability that someone both speaks a language that is greater than 1 language and at the same time is greater than or equal to 3 languages? Okay, so I'm just going to scroll back up here so we can take a look at the table. Okay, you can see here that someone speaking more than 3 languages would be the sum of those 3 probabilities together. Okay, if we add those 3 probabilities up, if I'm looking for the intersection of where does someone, and I'll just go ahead and change the highlighter here. These are all people speaking, it was more than one, so that didn't actually count one. Okay, let me go back to this. More than one language, so that would be these 4 languages here, speaking 2, 3, 4, or 5. Where does that intersect with someone speaking 3 or more languages? Well, that intersection is just right there where they're speaking 3 or more languages. So I'm going to add those probabilities up, and that's what I'm going to place in the numerator here. Okay, if we would add those up, I believe those add up to 0.075. And then in the denominator, we want to place just the probability of someone speaking more than one language. So we're not actually counting one language there. That would be the sum of these 4 probabilities, which actually totals 0.37. I'm going to divide those, and I get the likelihood that given that someone definitely speaks more than one language, the likelihood of them speaking 3 or more is roughly about 20.27%. Okay, and what I just said there is what we would want to write out for our interpretation here. Okay, the probability that, we need to make sure that we're being very specific with who we're talking about. Remember, this is a random U.S. high school student, so we want to say the probability that a student randomly, I should say a U.S. high school student, randomly selected, speaks 3 or more languages given he speaks more than one language is 20.27%. Okay, that would be our interpretation there. Okay, so let's take a little closer look at probability distributions here. Specifically with these random variables. Here we're talking about the probability distribution. These are discrete random variables, okay, because there are definitely gaps in between the values here. Okay, this is talking about tossing a fair coin, so a coin that's not loaded, it's not designed to land more on heads than it is on tails. It's a completely fair coin. We're talking about tossing this coin 3 times, and you'll notice here it mentions that our random variable x is going to be the number of heads that you get when you toss a coin 3 times. Okay, that's definitely something numerical, so it's certainly a random variable. The reason it's discrete is because if you're tossing a coin 3 times, the only values that you could get for how many heads you obtained is either 0, no heads at all, 1, 2, or 3. You'll notice there are definitely gaps between 0 and 1, between 1 and 2. Okay, it's not some type of continuous flow where you're including all the decimals and all the fractions in between those. Okay, so once again, x is our random variable, and the second row here represents the probability of that. Okay, you can see I made kind of a little situation over here off to the side showing here is where your random variable would be 0. Okay, and it's the one scenario where you get tails, tails, tails. Okay, there are actually 3 different ways of getting one head. Could have been on the first toss, or the second toss, or the third toss. And so for that reason, there are 3 different options for the random variable of number of heads being 1. And you can kind of see how I played out each of the different scenarios. When you go through and add up all the different combinations of what you could get for getting heads and tails on 3 tosses, you see there are 8 possible options. That's why my denominator here in the probability distribution is 8. Okay, so these are the 4 chances here. Okay, and you can see how there's a higher likelihood of getting just 1 head or 2 heads because there were 3 different scenarios resulting in that. That's why those probabilities are 3/8. Okay, but these still all add up to 8 over 8, okay, which is 1, which is what it takes to be a legitimate probability distribution, and each of those individual probabilities are between 0 and 1. Okay. All right, so let's go ahead and take a look here at the next page here. Okay, this is where we're going to wrap up this video just with this last example here. It's talking about describing a probability distribution. It says when we're analyzing discrete random variables, we're kind of following the same strategy that we used way back in chapter 1 when we were wanting to describe the shape and the center and the spread of a distribution, okay, as well as identifying any outliers. Okay, we had always used that acronym CUS. Okay, so we want to keep that in mind as we are looking at this probability distribution. Okay, essentially they're giving us whatever our discrete random variable is along the x-axis, and then the likelihood, the probability of that occurring here is on the y-axis. So here's what we're talking about in this example. It mentions at birth, and this is true, doctors do this, at birth there are a series of tests that are given to babies that result in a score of their overall health, and we call that score an APGAR score, okay? You can see in both the probability distribution that's in the form of a table as well as the one that's in the form of a histogram here, the likelihood of what the likelihood is of these APGAR scores for newborns. Okay, it seems like the higher the rating, okay, the more healthy the baby is. Okay, so here's what we're asked to do. It wants us to mention that APGAR scores of 7 or higher are where we kind of fit where a healthy baby should be falling. Okay, so before we calculate this probability, we're going to go ahead, this is great review from chapter 1, and we're going to describe this probability distribution looking at the graph. Okay, and again, we're just going to kind of run through that CUS acronym. Okay, so certainly it looks like the shape of this is skewed left. Okay, and so we're going to say it is skewed left. Okay, and I'm just going to add a little bit of context here, indicating higher APGAR scores are more common. Okay. Okay. Of course, we know that if there's more values on the right side, then more of the babies are having the higher APGAR scores, which is what we would expect. We would expect most of the babies that are born to be healthy. Okay. Okay, let's go ahead. So that checks off the shape. Okay, we'll let that be shape. Okay, now we're going to talk about the center. Okay, a lot of times you can use the word typical to really just mean the center here. Now, please keep in mind that if we're talking about this shape being skewed, a median is a much better way than a mean to be describing the center. Okay, we don't actually have the individual values anyhow, so we're going to say a typical APGAR score is approximately, okay, and I want to be able to say what this is. I definitely want to use the median. Okay, so how could I get the median by looking at this? Well, I can see what the actual probabilities are here. I need to work my way over until cumulatively I've made my way to the 50% mark. And I can either work from right to left or I can work from left to right. But as you add the probabilities together, I think you end up landing at roughly the 50% mark is somewhere here at an APGAR score of 8. Okay, as you add either all of these up or you come from the right, the 50% mark is at 8. So I'm going to say a typical APGAR score is approximately 8, and I'm showing that I'm citing the median there. Okay, so that takes care of the center. Okay, let's go ahead and address the spread. Okay, I'll just go ahead and say that the scores span from 0 to 10. Okay, that's how it's spanning, with scores that are 6 or under occurring rarely. Okay, now how did I decide on 6? Okay, that was kind of like me mentioning maybe unusual values there. Well, remember that 5% benchmark that we talked about earlier? We said anytime something has a 5% or really under a 5% likelihood of occurring, that's when we say that it's just really considered very, very rare or unlikely to occur. Okay, so if I go through, I can see that this is under 5%. These are all under 5% until I get to an APGAR score of 7. So that's why I'm considering all these APGAR scores that are either 6 or under, that those are occurring very rarely because they are underneath that benchmark of 5%. Okay, and then the probability question itself down here is actually quite simple. It wants to know what is the probability of an APGAR score being greater than or equal to 7. Well, we certainly could just look at our probability distribution here in the table format. We could just go through and just kind of cumulatively add up the probabilities of getting a score of 7, 8, 9, or 10. Okay, and we discover that basically there's a 90.8% chance